My name is again Chen Kim, and it's my great honor to make this presentation today. And I also welcome you to Korea, and I hope you enjoy this symposium and also enjoy your stay in Korea. This is very, I think, beautiful period of time in Korea. Okay, in my presentation, I will introduce the phantom conversion project in ICRP Committee 2, in which we try to convert the current Voxel type ICRP reference phantoms into a polygon mesh format to address some limitations of those phantoms in some dose coefficient calculations. But before I start my presentation, I will first briefly introduce the Voxel geometry. What is Voxel? The word voxel is contraction of a volume and pixel, and in two-dimensional space we have pixels, and likewise in three-dimensional space we have voxels. And we can use these voxels to construct models. If you use small voxels, then we can develop very detailed and precise models. But if we use large voxels, then we can just develop just a coarse model. Even though this voxel geometry has been the geometry of choice for the past 30 years, the voxel geometry has some limitation. And first, it's very difficult to construct a voxel model with the thin layers or small structures. For example, to define a very thin layer in a voxel model, the size of the voxel should be less than the thickness of the thin layer, which is quite often not practical if the layer is very thin. And the voxel geometry is not deformable, which means we can develop only rigid model, not deformable model using the voxel geometry. Okay, let me start my presentation on our phantom conversion project. And this slide shows the ICRP 110 or ICRP publication 110 reference phantoms, which were adopted by the ICRP and ICRU in 2007 recommendations. These phantoms are now these days used for organ dose and effective dose calculations. These phantoms are developed using whole body CT data of male and female patient and quite realistically represent the organs and tissues in the human body. But these phantoms have some limitations. That is, these phantoms cannot represent the organs and tissues if these are thin or complicated or very small. This is because in these phantoms, the organs and tissues are defined by voxels, and the problem is that the voxel size is not, the size of the voxels are not small enough. For male phantom, the voxel size is about 2 millimeters by 2 millimeters by 8 millimeters, and for female phantom, the voxel size is a little bit better, but still is about 2 millimeters by 2 millimeters by 5 millimeters. With these large voxels, some organs or tissues cannot be properly modeled because of the size. Okay, these are the skin models of the current voxel type ICRP 110 reference phantoms. If you look at the skin from the front side, it's fine, but if you look at the skin from other directions, then we can easily see there are a lot of holes which can cause serious problems in dose coefficient calculation for the skin itself and for some other organs like breast. We have some problems with some hollow organs. And it's about the respiratory tract organ. And in case of a respiratory tract organ, the target layer is very thin. And this slide shows the ET1 region. And this is a target layer. And the thickness is only 10 micron. And this cannot be modeled in the current voxel type ICRP phantoms simply because in the current phantoms, the organs and tissues are defined by the voxels. So an additional stylus phantom was used for SF calculations for weakly penetrating radiations. The situation is same for the ET2 region and large BB and small BB regions, and 3 additional stylized phantoms were used for SF calculations representing these tissues. Also, again, the situation again is same for the alimentary tract organs, and in this case, 7 additional stylized phantoms were used for SF calculations for weakly penetrating radiations. This slide shows the eye models of ICRP 110 male phantom, and the red part, these are lenses of the eyes. And as you can see here, the lenses of the eyes are directly exposed to air, which is anatomically incorrect, resulting in significant overestimation in lens dose calculation for weakly penetrating radiation. So ICRP again use the stylized phantom to calculate lens dose calculation, and this is the stylized phantom used by the ICRP for lens dose calculation. So if I summarize here, ICRP is not using only ICRP reference phantoms. ICRP is now using at least 12 additional stylized phantoms to calculate the internal and external dose coefficient, which is not only very complicated and error prone, but also could result in less consistency in dose calculation. There are some other limitations, but I'll just skip these. So these limitations and problems were discussed in ICRP Committee 2 meeting in 2013. Excuse me. And the committee decided to start a research project to convert the current Voxel type ICRP 110 reference phantoms into high quality polygon mesh format to address these problems. And a working group was established at Hyeong University in Seoul, Korea in December 2013. And a steering committee was also established in May 2014. And in this steering committee, we have Maria Jankel and Nina Patucci. They are the developers of the current Voxel type ICRP 110 reference phantom. So we are working together in the project, and we are making quite good progress. Also, necessary research fund was also secured in December 2014. So here is the objective of the research project. The objective of this phantom conversion research project is to produce exact replica of ICRP 110 reference phantoms in a high quality polygon mesh format, and the developed phantoms will include continuous and fully enclosed surfaces for skin, stomach, gallbladder, and urinary bladders, and also other organs. And also, these phantoms will include thin target layers in the alimentary and respiratory tract organs, and also include detailed and more accurate models for skeletal systems, eyes, lymphatic nodes, blood vessels, etc. So until now, I explained the motivation and objective of the phantom conversion project, and now I would like to give some brief explanation on the current progress of the project. So I divided my presentation into 4 subtopics, and these are about the construction of simple organs, skeletal systems, complex organs, and also preliminary result. And this is first about the construction of simple organs. To construct the polygon meshing model of simple organs, the Voxel model of the ICRP 110 reference phantoms was just directly converted to the polygon mesh format. And for this, we developed 2 methods. And this is for really simple organs, and one more method. This is for a little bit more complicated organs. And only difference that in this case, in this second method, we involve nervous model. We also developed and also adopted some adjustment and monitoring method. and to adjust our polygon mesh models to the original Voxel models, and also developed acceptance criteria for adjustment. And we are using two acceptance criteria. One is dice index, and that is volume, simply volume overlap fraction of two different objects to declare it as a successful conversion. The dice index should be greater than 97% of maximally achievable volume overlap fraction. Sorry. We are also using centroid distance to be declared as a successful conversion. The centroid distance, which is simply the distance between the centroids of two models in comparison, should be less than 0.5 millimeters. So here are some examples of a conversion and adjustment. And this is the Voxel model of the heart in the ICRP 110 reference phantoms. And this is the polygon mesh model of the heart, which is produced from the Voxel model. Then we compare these two models, monitoring the dice index and centroid distance. And in this particular case, the dice index was okay, but the centroid distance was too large. It was 0.59 millimeters. So we adjusted this model to the Voxel model, monitoring the dice index and centroid distance, and then finally the model passed both of the acceptance criteria. So we have some examples, but anyway, basically we use the same approach for the simple organs. And this is about the construction of skeletal systems. For simple skeletons, we use the same approach which was used for simple organs, and these are some examples. Thank you very much. These are some examples. And we have in case of cranium, excuse me. Yeah, sorry. In case of cranium, the cranium was a little bit complicated, but we used the same approach. It took some time. I think it took about more than 1 month just for this cranium. But anyway, we used the same approach. In case of the ribs, each of the ribs was converted and adjusted individually. Okay, in case of the spines, we used a little bit different approach. First, we tried to convert the Voxel model of the spine to polygon mesh format, but the result was not really very good. It was not very satisfactory. So we selected a high-quality polygon mesh model, and these models were precisely adjusted to the Voxel model. So I'll just skip these. Now it's about the construction of complex organs. The construction of complex organs are quite challenging and time-consuming, and in this case, I think we finished about only 50 or 60% of the planned work by now. In case of the eyes, we were successful. We successfully produced the polygon mesh version of detailed eye models, and also we successfully installed these eye models to the polygon mesh phantoms. The lymphatic nodes of ICRP-110 alpha phantoms cannot be directly converted to polygon mesh due to the complexity of the structure. So in this case, we have developed a computer program to generate the lymphatic nodes in the polygon mesh version phantoms, following the procedure which was used to develop the ICRP pediatric phantoms. Small intestine. It was one of the most challenging tasks in our project to produce a small intestine model. For this, we developed a dedicated computer program based on random work, and also we produced some procedure to generate small intestine models. We are basically generating 1,000 random small intestine models and getting the best one. We are also working on lungs and muscle, and in case of muscle, it's almost done. And blood vessels, this is not easy. I think it will take some time. Even though we are in the process of developing polygon mesh versions of ICRP 110 reference phantoms, we still have some preliminary results. And these are the original Voxel type ICRP 110 reference phantoms, and these are the polygon mesh version of these phantoms, which are produced from the Voxel phantoms, and we can see the improvement here. And this slide shows the skeletal system of the male phantom, and it's for female phantom. These are the hands and feet. Okay, this slide shows detailed eye models which are installed in polygon mesh version phantoms. This is alimentary tract organs. In case of alimentary tract organs, the thin target layers were also defined. Here is an example. This is oral cavity, and oral cavity we have the target layer, and target layer is only 10 micron thick, and this 10 micron thick target layer is now installed. It's modeled in the model, and this is for esophagus. Again, this is 10 micron. In case of respiratory tract organs, we didn't finish yet, but now we are working on it, and I think within a few weeks, I think we can finish. And the organs itself have been finished, but now we are working on the target layers. I think it will take a few weeks. And lymphatic nodes, and some other organs. So this is the developed phantom. It's polygon mesh version phantoms converted from the ICRP 110 reference phantoms. And these are still preliminary results. So still we are in the process of developing ICRP polygon mesh versions of ICRP 110 reference phantoms, but we are doing those calculations. These are mainly to confirm our approach for skeletal systems and also for complex organs. But I'm not going to explain these, but at least I can say that our result shows that the polygon mesh version phantoms are providing very similar dose values when compared with original Voxel phantoms, original Voxel type ICRP 110 reference phantoms for highly penetrating lesions, and also some more accurate or crack those values for weakly penetrating lesions. So here is the conclusion. Currently, we are developing Polygon mesh versions of the ICRP 110 reference phantoms, and the final versions of the developed phantoms will include continuous and fully enclosed surface for the skin, stomach, gallbladder, urinobladder, and also thin target layers in the respiratory and alimentary tract organs, and also the developed phantoms will include detailed and more accurate models for skeletal systems, islands, lymphatic nodes, blood vessels. Also, we just add detailed models for hands and feet. The developed phantoms will provide very similar dose values with the current ICRP 110 reference phantoms for highly penetrating radiations. And at the same time,